Suppose you have 4 different objects, for example 4 puppies, and you want to choose exactly 2 of them because your mom doesn't let you have more than that. The number of ways of doing such operation is denoted as 4 choose 2, and this notation is called the binomial coefficient. Generally, the number of ways of choosing k objects from a group of n objects is denoted as n choose k, and it is given by the factorial formula, which you can see right now on the screen. So in our example, there is exactly 6 ways of choosing 2 puppies from a group of 4, which can be illustrated by pointing out these exact ways. Binomial coefficient has more to offer than just a help with choosing puppies. For example, as the name suggests, these numbers are the next coefficients in the binomial expansion of x plus y to the power of n. N choose k also denotes the number in the nth row and the kth diagonal column in the Pascal's triangle. And there are lots and lots of other identities related to the one and only binomial coefficient. The fact about all of these things is that they can be proven algebraically, and there is nothing wrong with algebraic proofs. In fact, they are completely valid and acceptable mathematical proofs. The thing is, they tend to be not very intuitive. If you would see an algebraic proof of this identity, it would indeed be very short, but it wouldn't tell you why essentially this identity is true. Instead, we would like to take it and show that the left and right side of this equation represent the same thing in the language of choosing some objects from a larger group of objects. Such proof is known as combinatorial proof. To showcase the power of such proof, let's prove just mentioned identity in 2 ways, algebraically and combinatorially. We start our algebraic proof by taking left side of the identity and expanding it with use of the factorial definition of binomial coefficient. Now we can notice that n minus a factorial can be cancelled out. Let's rearrange it a little bit by swapping a factorial and b factorial and multiplying the whole thing by n minus b factorial over n minus b factorial. We can do it because this fraction is essentially equal to 1. The last thing we want to notice is that the first fraction is equal to n choose b, and second one is equal to n minus b choose a, and we are done. In our combinatorial proof, we also start with taking left side of the identity, but this time we want to interpret it with groups and subgroups. N choose a means that we have some group large n of n objects, and we choose exactly a elements from it and put them into the set large A. Then n minus a choose b means that we choose b elements from the set of untaken objects, which is exactly n minus a, and put them into a new set, which I'll call large B. We can notice that as long as sets A and B are disjoint and included in n, they can be whatever size you want them to be, so we can actually change the order of choosing these sets and firstly choose the set B, which will be denoted as n choose b, and then choose set A from n minus b, which will be denoted as n minus b choose A. Since these approaches count number of ways of choosing 2 separate sets inside another set, they must produce the same answer, and that's why our identity is true. Now let's prove the second identity related to binomial coefficient. Left side can be of course interpreted with choosing n objects from a group of 2n, but that's not the only way of describing such situation. We can split the 2n group into 2 n subgroups, and let's call them x and y. The choice of n elements must contain some objects from the x and some objects from the y. So let's break it down to cases. If our choice contains 0 elements from x, then it contains n elements from y, where this action is represented by n choose 0 times n choose n. If it contains one element from X, then it contains n minus 1 elements from Y, and so on. Since these cases are disjoint, the total number of choices is represented by this sum. The last thing we want to notice is that for any number k, we have n choose k equals n choose n minus k, which follows from the fact that choosing k objects from a group of n also creates second group, which contains n minus k objects, so there is one-to-one correspondence between these two types of groups. Having this identity, we trivially see that these two sums are equal, and hence our final identity is true. It actually turns out that this equality is a special case of the main star of this video, the Vandermonde identity. It looks exactly like this. Vandermonde's identity is the best example of showcasing why combinatorial proofs are much better than algebraic ones. If you were to prove it with algebraic transformations, you would require things like binomial theorem, a formula for a product of polynomials, and a lot of spare time. Let's just agree it is ugly. On the other hand, combinatorial proof is very elegant and similar to the one we just gave for the second identity. So let's go ahead and prove Vandermonde's identity with the combinatorial proof. Once again, we start by noticing that m plus n choose k means that we choose k objects from a group of m plus n objects. In the second identity's proof, we tried to look at this choice from other perspective, and we splitted the 2n group into 2n subgroups. In this case, we are splitting a m plus n group into two subgroups, one of size m and one of size n. Then we construct the same argument as earlier. We want to choose k objects, some of them will be in the m subgroup, and the rest will be in the n subgroup. Summing up all these cases, we get this beautiful sum, and we are done. To sum up, if you want to prove an identity which involves binomial coefficient, before reaching the definition, try proving it combinatorially first. Thanks for watching.